Well, hello, AP Physics students. Chapter 6. We are on to Chapter 6 already, Work and Energy. And by the way, a lot of students, if you ask them at the end of first trimester physics, what was the toughest chapter in first trimester? A lot of them will say Chapter 5, all right? And if you ask them what the easiest chapter is, a lot of people say Chapter 6. So anyway, if you think physics has been tough, it is tough stuff, but a lot of people think Chapter 6 is when stuff really starts to come together. So, hang in there. You guys are doing great work. Speaking of great work, let's get going. Let's put some energy into our little lecture here. All right? So, physicists mean something very specific when they talk about work, okay? In physics terms, work is done on an object when a force acts on it and moves the object through a distance. Okay? So here is my pen. It is sitting right there. I am going to exert a force on my pen, and as I exert this force on the pen moves through a distance. So I have just done work. All right? Exerting a force on an object moves through a distance, we call that work. Your book defines work in a formula as the parallel component of the force times the distance. Here, this means that the force must be acting in the same direction. Another way to say it is FD cosine theta, where theta is the angle between the force and the distance. Okay? Note that the force and the distance must be in the same direction in order for work to be done. All right? So the force you're pushing with and the distance the object's going through have to be in the same direction in order for work to be done, or positive work to be done. As we'll see in just a second here. All right. Both work and energy are measured in joules, named after James Prescott Joule, who did a lot of pioneering work in energy and thermodynamics. 1 joule is equal to 1 Newton meter. All right. So if I were to exert a force of 1 Newton on an object and push that object through a distance of 1 meter, we would say that I had done 1 joule worth of work. Okay? Work is a scalar, all right? But it can be positive, negative, or zero. So work doesn't really have a direction associated with it. It is not a vector. It's a scalar, and it can be positive, negative, or zero. And let's take a look at that. When is work positive? If I exert a force in this direction and the box moves a distance d in that direction, that is positive work. All right, the force and the distance that the object moves are in the same direction. Now, let's say an object is moving this way, okay? And I exert a force on it this way, maybe in an effort to slow it down, okay? That is negative work, right? So when F is in the exact opposite direction, that is negative work. And of course, if an object is moving in a certain distance, and I exert a force perpendicular to that, the work here is zero. No work is being done. If you just plug in this angle here, this will all work out. For instance, if the angle is 0 degrees here, cosine of 0 is 1, so it's just F times D. If this angle is 180 degrees, then cosine of 180 is negative 1. So again, FD cosine works out. And if this angle is 90 degrees, cosine of 90 is 0. So anyway, our formula checks out there. All right. Now, why did we define this idea of work? As it turns out, the physics we've been learning doesn't always work to solve problems, and sometimes it's a lot easier to define. Just think of things in terms of energy to solve problems when our regular forces and kinematics and Newton's laws don't work for us. All right. Okay. Well, how about an example problem here? Let's look at problem number 5 from chapter 6. And this problem states that I have a 5 kilogram object. The box is resting on the floor. Let's define to be to the right to be the positive direction. And there is some force that acts on the object, and it accelerates the object at 2 meters per second squared for 7 seconds. And we want to know how much work, what is the total work, sometimes called the net work, done on the object. Well, as always, start with your free body diagram. By the way, be careful in these problems now. Sometimes I will have weight in a problem and I will have work. So sometimes if I'm dealing with work, I'll call weight mg in my force diagram here instead of using W for weight. Okay, so how about I don't use extra arrows here? So I have a normal force, I have weight, I have some force pushing this way that is accelerating my object. What is the work that is done on the object here? Well, to find the net work or the total work done, I would need to find the net force, okay? And by Newton's second law, I could say the net force is equal to the mass times the acceleration. And I would know the net force and the acceleration would have to be in the same direction, which would be to the right here, this way, as I've defined it. So I would take my mass times my acceleration and find out that the force, the net force on the object is 10 newtons, okay? 10 newtons. So I am halfway there. However, at this point, I do not know the distance that this force is exerted through. And like many problems in physics, you might have to go back to a previous chapter to find things out. For instance, the distance it might travel through, I might call that distance x. And I think if I use just a little bit of one dimensional kinematics, right? Our good old friend from chapter 2, we could get something like this. So if I say the box starts at 0, the problem said it's starting from rest. 1/2 times 2 times 7 squared, right, would be 49 meters. So in 7 seconds, the object is pushed through a distance of 7 meters. Pardon me, distance of 49 meters. So this is what I'm going to use for my D in my FD cosine theta. So the work then, as we said, is FD cosine theta. Theta is just going to be 0 degrees here. The force and the distance are in the same direction. So this would be, I'm running out of room here, 10 newtons times 49 meters. And that would be 490 joules would be my answer there. Boy, just had enough space there. So the total work done on this object is 490 joules. Okay. All right. Well, nice work, physics students. If you have questions on that, discuss those in your group tomorrow. And for your joke today, we're going to talk a little bit about snail racing, okay? Snail racing. So I do some snail racing, and I thought I could take the shell off of my snail, and he would go faster because there's less weight. But as it turns out, when I took the shell off my snail, he was just more sluggish Get it, slug, because like you take a snail, you take a slug. I don't know if that's like biologically correct or not to call it slug, but anyway, nice work, AP Physics students. We'll see you tomorrow.